Mm, no? Okay. So basically, you don't need DH parameters per se to solve robotics. They are just a convention actually to standardize how we express the frames that are attached to our yeah, to our robots. Okay. Yeah. So I will call this as link I minus one. Okay. This middle one as link I, and the next one as link I plus one. Is that fine? Okay. So I don't think there would be a problem till now, but where the difference arises is now what do you call this joint? Is it the joint I minus one or I plus one? Right? Wait, is somebody saying anything? Okay. Okay. No, nobody's saying. Yeah. So I think what sir might have told you is that um, we can use, yeah. No, what? So what we will use is that we will say that the joint between link I minus one between link I minus one and link I is joint I. Okay. So automatically the link between I and I plus one becomes joint I plus one. Cool. So this axis that is aligned with the rotary part of the both of these joints is what I call ZI, since this is joint I. Okay, so the frame I is attached at this joint. Okay, and at this joint, okay, so the axis about which the rotation occurs here, okay, I call it ZI plus one. Okay, cool, that's so far. So these two axes, as you can see, in general case, can be non-parallel and like parallel but non-intersecting, right? So there would be a minimum, a line, the shortest line connecting these two parallel lines, right? Parallel but non-intersecting 3D lines. So this axis, right? So along this line is what we define as your x of I. Okay. So the x-axis of joint I. Okay. And you do similarly for I plus 1 using zi plus 2. Okay. So I will just assume that there is an xi plus 1 here, right? Is there any problem till now? Okay. No. Very good. So then how do you get the third uh, axis here? We have z, we have x. How do we get the y? Harsh, your voice is not clear actually. Harsh, can you try typing? What do you want? What you want to say? Okay. So we simply need to do a cross product actually of z and x. Okay, because we know that we use a right-handed coordinate system. Okay, always in science. That is one more convention that we have chosen. We could have chosen to use a left-handed coordinate system, but we just chose to use a right-handed coordinate system. So according to the right-handed coordinate system, y-axis is in the direction of z cross x. Okay, perpendicular to both z and x, and in the direction that is given by the right-hand rule of the cross product. Okay, so this is yi. Oh, what is this? This is a general manipulator. Wait. So you must have seen some manipulators like this, right? Let's say, yeah, this. Okay, and there is some gripper or end effector here, right? So these are planar manipulators. They are in 2D and they are uh, very, not limiting, but there are some assumptions that the links are straight, okay, they are not curved, and all the joints they lie along the same axis, that is a vertical. Okay, now this what I have drawn here is a general case of the same thing. Okay, so here I have drawn links to be rigid but non-straight. Okay, so these can be curved in any way, and these axes, these joint axes can be non-parallel. I mean, they're parallel, but they're non-intersecting. Okay, so they can be aligned differently. They need not be aligned in the same direction as well. Okay, so this is just a general case. Okay, this one is just a general case of what you might have seen in examples. Is that fine? Okay, so this distance, this shortest distance that I just marked here. Okay, so this is called your link length. Okay, I will denote link length as Li, or you can even call it Di, or um, it doesn't matter. I think most people call it A of I. Okay, so it is just the link length. Okay, this shortest line segment. Yeah, the length of this shortest line segment along which we have attached Xi. Okay, and then you know from what sir had told you, you know that you had four parameters, right? You had um, AI, theta I, di, and alpha I. Okay, so I'll just, since I've told you how I'm attaching the frame, I'll just tell you quickly how these AIs and LIs are, they're all chosen. Okay, so this is the distance between zi minus 1 and zi. Okay, these are all unit vectors about xi minus 1. Okay, and this is called link length. This theta I is angle between xi minus 1 and xi about zi. Okay, so if I try to see from here in this diagram, then the angle between this xi and this xi plus 1 will be called theta I plus 1. Okay, and it will be measured along zi plus 1. So it will be measured along this axis. Okay, this next axis. Okay, this is just convention that we are choosing. Okay, so since we want everything in same indices I, so we have just changed these accordingly. Okay, and this is what we call as joint angle. Okay, and then you have your link offset. Okay, how much? Okay, how much are these two origins, apart from each other in the vertical? So, like, what does vertical mean? Along the z-axis. Okay, how much are these two apart? Okay, so it is distance between xi minus 1 and xi about zi. Okay, so this is what we call as, I think some people call it link offset also. Okay, like where is, this is the offset in the link. So how much offset this link I creates, okay, in the origins of the joints. You can call this also. Yeah. And the fourth parameter is what we call the alpha, okay, link twist. Okay, how much, how is this zi minus 1 aligned with this? How is this zi aligned with zi plus 1? Okay, so that is what we call link twist. Okay, so that is angle between zi minus 1 and zi. Okay, and this angle, every time you talk about anything, you need to specify about which axis, you're rotating or you're translating. Okay, because direction is important. So, and this is along x I minus 1. Okay, and this is called, I think, link. Is my handwriting fine? Can you all understand?
Yes, sir.
Oh, that is good. Okay, so this is the definition of DH parameters, or basically the DH parameter convention that we use according to as given in the book by J.J. Craig. Okay, so you can see that we had chosen each and everything here. Okay, like how we will define this AI, or not even just AI. Okay, how we will attach these coordinate axes, these basis vectors to their respective frames. Okay, this is all our choice. Okay, but now since we have chosen this, we have to be consistent with it. Okay, so you choose what convention you want to follow. Okay, I think that this one is easier because there are only two frames. Okay, that are of concern here, frame I and frame I minus 1. Okay, and in some conventions you need to take into account I I I minus 1, I and I plus 1, all three, to define you know only these simple parameters for two links. Okay, so from my experience, this one is simpler, but it is up to you what convention you use, and whatever you end up choosing, just stick to it. Okay, that will make your life easier. So is there any doubt in how we have defined this? Because if there is no doubt, I'll just take a question, because there is not much to tell you about a convention. No? Shyam, your voice is not coming actually. I could not hear what you said. Himanshu, can you see the screen?
Sir, can you explain the diagram once again, sir?
Oh, yes. Okay. So this diagram is, this whatever I have made this here. Okay. This, wait, I'll use a different color. Okay. This is just your link. Okay. Any link, and it will be attached, the joint will be made from the cylindrical portion. Okay. And then at the cylindrical portion, using the cylindrical portion of another link. Okay, this is just how I'm drawing link. This has nothing to do with real world, how links are there in real world. Okay, so this is another link. Okay, I've not made it straight because it is not necessary that your links are always straight. Okay, but it is necessary for this convention that our links are rigid, and we have assumed all of our links to be rigid. Okay, So there are these two cylindrical connectors, you can say, at the end of each link. Okay, but they do not, the axis of these joints, these cylinders, they do not point necessarily in the same direction. Okay, they can be twisted as well in any way they want. Okay, so this is a general case, for a link of a manipulator or a robot or anything. Okay, so now since I have these three links, as you can see, okay, what I have done is I've called them, I've given them names. So this is my link I minus 1, this is my link I, and this is my link I plus 1. Okay, and now is where my convention starts. I've chosen that the joint, okay, the joint between I minus 1 and I is what I will call joint I. Okay, this is what I have chosen, and not me. J.J. Craig had chosen, and he has told everyone that yes, you can also do the same. And so subsequently, the frame between link I and link I plus 1, it becomes joint I plus 1. Okay, so now these joints basically are your frames. Okay, joint means that what will you call this axis about which the rotation is occurring, or what will you call this axis, about which translation will occur in case of prismatic joints. Okay, so that is just for that. Now once you have decided that you will call this a joint I, so this is frame I, okay, you assign a z axis to this joint. Okay, so the z-axis is along the axis of rotation of the, of this joints, because these two cylinders, if they have to rotate, they have to be aligned, right? They have to be, face over each other. So yeah, their common axis is what I call as zi. Similarly, the common axis of link I and I plus 1 for joint I plus 1, I call zi plus 1. Okay, and then so these two zi and zi plus 1, these are parallel but non-intersecting. Okay, these are two lines in 3D space that do not intersect. And if they do not intersect, they must have a minimum distance between them, right? A line connecting them with the shortest possible distance. So along that line, okay, I will draw this in. Yeah. So along this line of shortest distance is where I define my xi. Okay. And similarly, there will be some x of I plus 1 for this next one. Okay. I've not drawn it because to make this xi, we needed zi plus 1. Okay. So to make this xi plus 1, I will now need some zi plus 2 here that I do not want to draw. So I just made it like this. Is that fine? Okay, and then using these two frames. So why I've only chosen Z and X and not Y, because now you can always get Y just by taking a cross product of Z and X. Okay, so this always holds for right-handed coordinate system. Okay, so this is cross and this is X. Okay, so is there any question now? No? Okay. So there is none, right? Like, can somebody just say a yes or no, like really quickly?
No question, sir.
Okay, yeah. So what we will do now is we will do an example. Okay, in this example, we will assign the DH frames, okay, for each of these frames, okay, for multiple links. So let me just make a picture. Um, not good at making pictures, so just bear with me. Hmm. Hmm. People are coming still. Okay. So one axis is here. Okay. Another is here. And then one axis is here. And you have another axis. Like this axis just continues. You have been given this initially, and this distance, okay, this axis to axis, center to center distance is what we call L11. Okay. And oh, okay, nobody. Yeah, and this distance here is what we call L12. Okay. And then this center to center distance, I am writing it because I do not have any space left up there. This is L2. Okay. And from here to here is, let us say this is D3. Okay. And a tool is here. Okay. That we just maybe want to rotate or, just let it be there. This is L4. Okay. So you can see this joint is a prismatic joint. Okay. And these two joints are revolute joints. You know about different types of joints, right? Does anybody here not know about different types of joints? Okay, you all know about different types of joints. Okay, so in this case, I am telling you that these are what these joints are. But if you get an equation and it is not written, then you have to decide for yourself that what kind of joint it can be for the given situation. In this case, uh, if I mark this 1, 2, 3, and 4. Okay, so 1, 2 are revolute, 3 is prismatic. Okay, this is what I am telling you, that 3 will not rotate, about this axis. It will just move up and down. Okay, and this there is another joint, 4 here at the point that I have made. Okay, I will mark it in red also. Okay, this is also a revolute joint. Okay, about this axis that I have marked here. Okay, about this green axis. Okay, this I've told you. Okay, so there is no confusion which joint is which. So now you can see that there are different rigid moving parts of this complete robot, right? And these single rigid parts of robots are what we call links. Okay, that I had drawn, like really in a really funny way here. Okay, so these are now simplified. These are just straight, very well cut out, not so twisted links. So now, what was the first step that we had to do here from what I told earlier? We had to first assign names or letters to this link, right? That what we will call each link. Okay, so can we identify what is the first link here? Yes. Yep. Anyone?
L1.
Uh, Yeah. So yeah, L1, but so I will do this. See this link, okay, this big cylinder around which this link has been mounted. Okay, this is grounded. This will not move anywhere. You can assume that this is the link on which motor is mounted here. Okay, so since this is my ground link, because this is has been grounded, as you can see from the image also. Okay, I will call this my zeroth link, link 0. Okay, or I will just write here 0. Okay, and then all the subsequent links I'll provide a higher, one number higher. Okay, so this number becomes link 1. Okay, this link becomes link 2. Okay, this becomes link 3, and this becomes link 4, right? And if you want to treat your tool also differently, then this becomes link 5, your tool. Okay, tool separately also becomes a link. So now we try to assign frames here. Okay, so let us do one thing. Let us assign the ground frame here itself. Okay, at just at the bottom of everything. Okay, and we will make all the frames with red. Okay, so this can be assigned arbitrarily, so I am choosing it such that it is how we know Cartesian coordinate systems, like how we have till now made it. X and y is in the plane, and then z comes outwards. Okay, and then I will make frame 1 here. Okay, so this becomes z1 because this is along the axis of rotation of this, and since this is z2. Okay, so this axis will now be x1. So you can see that in this case, this x1 is right along the length of the link. Okay, but that might not always be the case. Okay, so now if we have z and x, we can always have y by taking a cross product. Okay, so now since we have this, okay, we can come here also. Okay, so now since the next revolute joint is this, okay, so what we will do is we will assign a frame directly here. Okay, what we will do is we will take a z4 here. Okay, and now since you can see that I have to keep x and y perpendicular to the z. Okay, but there is no next z to um, align with the z4, so I can choose this x4 and y4 arbitrarily. Okay, I choose such that this x4 is in x4 and z4 are in the same plane, and this plane is the same as the 2D plane in which my problem is given. Okay, but y4, this was the third frame, right? Yeah, x3, y3, and z3. And then I can also assign a frame to our tool here. Okay, x4, y4. Oh, wait, I made a mistake in the y3 here. Yeah, yes, it will be out of the plane, y3. Same, y4. So, is there any doubt here? So, uh, I know that this looks slightly arbitrary, but what will convince you of this, that this is actually correct, okay, is when you try to identify these parameters here. Okay, so let us, so okay, so this I, okay, this I subscript is the link number. Okay, so let us try to write A0 in this case. Okay, so tell me what will be A0 in this case? Anyone? Yes. Yeah, so actually you do not need a frame at joint 3 because this is a prismatic joint, okay? And in our formulation, prismatic joint has already been encoded by the information of this DI, okay? So this is actually a thing that when you use the Craig convention, okay, that you do not need to specify prismatic joints differently, okay? You can, set your convention using only revolute joints, okay? But you can see, right, this any of these parameters can now change, okay? We had set these axes assuming only revolute joints, okay? But now since any of these parameters can change, I can change this di to um, make it a revolute joint, okay? And I can fix this theta, I make it just fix it at an angle, okay? So then it becomes a pure prismatic joint, okay? There is no revolution there, okay? But why I needed revolute joints here is to fix these ZIs, okay? So because in this case, um, I will use green now. So this was RZ2, okay? And this has become RZ3, okay? So the DI, okay, basically, you know, will be this, what was DI? It was the distance between the origins of two frames. Okay, now since one of my frame is here and the previous one is here, okay, so the distance between them automatically gives me the DI, and that is the prismatic displacement of this link. Is that fine, Pratyush? Okay, so now we can try and identify what is A for 0. Okay,
L not.
um, are you sure about that? Okay, so this length is I've given L naught, but will A naught be L naught? Does everyone agree
A
with
naught
this?
is difference between Z1 minus Z1 and Z0, right?
Okay, so for AI, this is the distance between Zi minus 1 and Zi about Xi minus 1. Are you confused that since there is no minus 1 frame, so how can we write this? Yes.
So then I plus 1. Okay.
Okay. So what I will do is I will tell you about something called a DH parameter table. Okay. That makes our life a bit easier while writing these DH parameters. Okay. Hmm. Yep. Okay. So what I will do is, I will give the link number here and the parameter here. Okay. So what are our parameters? They are AI, theta I, di, and alpha I. And, you know, so you can try to write it for link 0 also, like A0, um, alpha 0, theta 0, and d0. But since you know that if you try to even attach a free minus 1 here, there is no point in it, attaching the frame in any different orientation than frame 0. Okay, so you can say that I minus 1 frame is also coincident with frame 0. Therefore, all these parameters will also be 0. Okay, so that is why we directly start with link 1. Okay, like, so what is the A for link 1? Hmm. Nobody? Okay, so since this was the distance between zi minus 1 and zi, so in case of I equal to 1, it is between z0 and z1 about x0. Okay, so about x0 distance between z0 and z1 is what? 0. So this becomes 0. Okay, then we have theta. So what is theta 1? So theta 1 is angle between x0 and x1 about z1. Okay, so distance between x0. Okay, so I will use a different, yeah, distance between x0 and x1 about z1, right? Oh wait, that is angle. Okay, so I'll write di first. Okay, so distance between x0 and x1 about z1, so that is your di. Okay, so your d1 actually becomes L0.
Have you set up your computer?
Okay, so and what is theta? Can anyone tell me? Anyone? Like, I just want to know what is theta 1, and here is the definition.
Sir, it's 0.
um See, it's not, it will not be 0. And why it will not be 0 is because, see, I've told you that this z1 is the axis of rotation. Okay, so now assume that link 1 starts to rotate about this axis z1. Okay, so now if you look from above, okay, and this link starts to rotate, the x1 axis, okay, now let's assume this is from above, and this is x0 and this is x1 initially, and when link starts to move, the x1 makes an angle uh, from the x0. Can you, do you agree?
Yes, sir. Yes, sir.
Okay, so in this case, if I call the angle of rotation for angle 1 as theta 1, okay, theta 1 is from x0 to x1. Okay, so this theta, okay, here will be theta 1. It will be a variable. Okay, and finally, what will be alpha 1? Okay, so alpha 1 is angle between z0 and z1 about x0, right? So what is the angle between z0 and z1 about x0, right?
Minus
Okay,
theta
so
1.
uh, yes, so actually what you need to do is that you assume that what is the rotation that you need to give about x0 such that z0 goes to z1. Yes, Pratyush, it will be minus 90. Okay, you need to rotate about x0 such that z0 coincides with z1. Okay, so this angle is minus 90 or minus pi by 2, minus 90 degrees or minus pi by 2 radians. Okay, so now you have 4 parameters for link 1. Okay, similarly, we can write parameters for link 2, link 3, link 4, or if you have attached, if you have considered your end effector. Oh, so link 4 is our end effector itself, so it doesn't. But yeah, if you attach any different frame, even after 4, okay, you can do this. So now why I've told you this table is because it will be used, to form the homogeneous transformation matrices that you had seen in the last week lectures from the DH parameter table. Okay, and this is where DH parameters come into play. Okay, because you all know that to find the homogeneous transformation matrix, you need to first need to know the yaw pitch roll rotation of each body with respect to the other. Okay, and then you need to know the translation also. Okay, so if everybody does it differently, okay, it will make it very difficult to communicate. Okay, what actually the results are. Okay, what let us say that I use, for orientation, let us say I use yaw pitch roll, but let us say that Pratyush here he says that no, I will use, roll pitch and yaw. Okay, then if we try to match our data, it will not match because it is not standardized. Okay, we are using different conventions. Okay, so that is why the DH convention is a way of standardizing a way to calculate your transformation matrices such that if you have written these parameters correctly, your matrix will always be the same. Okay, your transformation matrix will always be the same. And how you calculate this? Okay, because then using these parameters, you have a closed form expression, basically a formula for transformation matrix, this TA in terms of all these parameters. Okay, and I think sir will cover that in next week's lectures. So I will only tell about that formula or closed form expression when sir discusses it. And I think this is what sir had discussed in week 2 overall. So are there any doubts in this session or in general in week 2 or in any assignments?
Yeah, just one question
Yes,
regarding this Z0 axis,
yes,
right? So the first link, which is attached to the base,
yes,
yeah, is rotating, is having a kind of circular motion, right?
yes.
It's not in parallel to the base, but it is circulating over base, something like that, right?
Yeah, it is rotating like this. Okay, so
Yeah.
this is
So
your base and this link one is going around like this.
right. So Z0 shouldn't be parallel with the pillar or the link one.
No, no, that is what I was telling you. This is my ground frame. Okay, so I am just putting my ground frame where I want it to be. Okay, now where my convention comes into place from the frame one.
Okay.
Okay, so I only am concerned with where do I put my frame one. Basically this is your first joint, right? This is your joint one. This is your second joint. Okay, so
Okay. So
I
what we are saying that this base link one is fixed on the ground. It is not rotating. Yes.
yes, it
Okay.
is your
Okay.
base frame, it is your ground frame. Okay, we have put it here
Okay.
because we want to put it here because I wanted to generalize this case, because usually we draw 3D frames like this, right? That x and y in the plane of the problem and z coming outside of the plane of the problem. Okay, so yes, you can keep make this as z0 and then keep y0 here. Yeah, you're free
Hmm.
to do that. Okay,
Okay.
but
Then in
if
that case, the values of theta one, d1,
yep,
etc., will change a little bit.
um no, actually, you can try. See,
Okay.
see, theta 1 will not change. I think that alpha might change.
Huh. Means not all parameters, but
Yeah,
some value of some of the parameters will change.
yeah, sure. That is for sure. That will change. But because see, theta and d are actually the what gives your robot the motion that it has. Okay, so in most of the cases, changing the frame should not change these parameters. If it is changing these parameters, then maybe you are not assigning the frame at a proper place. Okay, and it might make things hard, as you go forward.
Okay.
Yeah. Any other questions from the lectures from week 1 assignment, or with respect to its own frame of reference with the okay, I think this is related to the last question of week 1, right? Okay, so
Sir, yes, sir. The last one and the eighth question.
actually I don't remember like what is the eighth question and what is the last question. I had just seen it once, so I'll tell first this what about this doubt. Okay, so science maniac.
Sir,
Uh,
I'm Ishwar, sir. Sorry, sir. I forgot to change the name.
it's fine, it's fine. I don't mind. Okay, so let us say that this is your okay robotic tool tip. Okay, and this point is what I'm calling tip. Okay, is this fine?
Yes, sir.
Okay, so I've told you right that we can assign frames here also to this tip. Okay, now you can see this tip can also, I'm saying that this tip can also rotate about this point, basically the axis coming out of this point. Okay, so I can assign a frame here to this tip, right? I can say that this is X, this is Y, and Z is outside the plane. Okay,
Yes, sir.
so this and see, were you there in the last class that I took on 30th of July?
Sir, no, sir. I joined late, sir.
Oh, it is completely fine. So see, whenever you say that you're defining a frame, okay, okay, I will give you the general example that I gave in the last class. Okay, let us say that this point, this origin, I denote with capital letter A, and I have three braces vectors like this, E1, E2, and E3. Okay, so these four constitute a coordinate frame. Okay, and I use italicized A to represent a coordinate frame, and this, is what I'm writing here is how you represent a complete coordinate frame. Okay, if you miss one, then it is incomplete information. Okay, you need to specify where your origin is. Okay, in order to for it to be a valid coordinate system. Okay, now for this robotic tooltip example also, this origin we have specified. Okay, that this origin is right at this joint for this robotic tooltip. Okay, so now when I talk about the position of the robotic tooltip, I talk about the position of the origin of its frame as seen from ground frame. Is that fine?
Yes, sir.
Okay, so now, but tell me, what is the position of the robotic tool tip in its own frame?
Sir, like
Yes,
it's 0, 0 because
of course,
it's in
because it
the.
is the origin itself.
Yes, sir.
Okay, so now let us say that I denote it as R, uh, let us say T for tooltip. Okay, so if it is with respect to its own frame, so that is just the origin, because this is how I've chosen it to be, right?
Yes, sir.
Hmm? But now if I want to write it in the base frame, hmm? Okay, and this vector, okay, you need to specify if it is written in which frame. Okay, if it is written T frame or it is written in B frame. Okay, B, or I'll use G for ground frame. Okay, you need to be very, strict about that, in which frame you're writing this. So now if I want to write this T G, okay, so now when I write this vector, this is the vector I'm talking about. Okay,
Yes, sir.
okay, so now this vector also, you can write in any frame you want. Okay, it is not compulsion that you write it in G frame only. You can write this also in T frame. Okay, and to convert from G to T frame, that is where the rotation, the concept of transformation matrix came, right? Do you remember this? Okay, if I have a vector represented in some frame, I can multiply it by the transformation matrix that takes from one frame to the other frame, and this act of multiplication, the result will give me the representation of the same vector in the another reference frame. Okay,
Yes, sir. I got it, sir. Yes, sir.
okay, so what you need to do if you want to find RTG in frame G, okay, so you need, in frame G you need, okay, and you can say that you have, you know the RTG in frame T, right? Okay, did you understand what I just did?
Sir, can you repeat that one, sir?
Yeah, so just take it like this, okay, because these transformation also contain the information on the translation, right?
Yes, sir.
Okay, so basically you can also remember this if you want to get the position of the tooltip with respect to ground frame. Okay, what you can do is you can multiply this transformation matrix with the origin, with the 0, 0 vector, because that is the position of the tooltip in its own reference frame. Okay, so basically that is how you take the position from its own reference frame to the ground or any other reference frame.
Yes, sir.
Yeah, so Pratyush, yes. So these are the four. We see. Um, this is not the minimum number that we need. Okay, minimum set of kinematic parameters, because what we want to represent is that we want to represent the pose or the position and orientation of each and every body in space. Okay, so let us say if there is one body, how many parameters do you think you need to specify its both its position and orientation in 3D space? Yes, Pratyush or anyone else?
Four.
No, you need six. Okay, why six? Three for the position and
And
three
three
for
for
the
rotation.
orientation. Okay, so if the bodies are unconstrained, okay, then you need six for each body. Okay, but now if you start constraining these bodies, okay, and you say that each body is constrained at two positions in independent directions. Okay, if that is the case, then you're essentially constraining 2 degrees of freedom. Okay, so in that case, how many are left? Four. Okay, so what I had drawn here also, I have constrained this green link at two places, and these constraints are in independent directions, right? Because Zi and Zi plus 1, do they intersect anywhere? No. Okay, so given this constraint for link I need 4 parameters. Okay, and now if I fix some of these 4 parameters also, okay, because of course, as sir had said in the lectures also, that you will the out of these four only one will be the variable. Okay,
Yes, sir.
that is usually the case. Okay, that you have either a revolute joint or a prismatic joint. Okay, but if you okay, so that is how you make 1 degree of freedom joints. Okay, you constrain it until you're remained, you're left with 1 degree of freedom only. Is that fine? But if you constrain it such that you have a revolute joint but also a prismatic joint attached to that, so now this link is a 2 degree of freedom system. Okay, you can analyze it, there is no problem. Okay, but you have to keep this in mind that what you have been told till now is a simplified version of slightly more complex, situations. Okay, so 4 is not the minimum. Minimum is decided by, your number of variables. How many parameters, independent parameters you need to completely define the configuration of this robot or any machine or any system. Is that fine? Pratyush, mic is not working. I'm sorry.
Hello, can you
Yeah.
listen
Oh,
me?
yeah. Now it's working. Yes, Pratyush.
Yeah, yeah, yeah. I mean to say that whatever we are reading DH algorithm, is it for 1 degree of freedom?
No, actually, see, you have seen that we have used these parameters here, right, as variables: a0,
Yeah,
alpha 0, theta 0, and d0,
yeah,
right? So currently, you can say that uh, what you have learned right now is for 4 degree of freedom systems. Okay, 4 degree of freedom links. Okay, for system you need to talk about the complete degrees of freedoms. Okay,
correct.
yeah, but this is for the general case when all of these are changing.
Okay,
Okay,
as per teacher said that we are moving out means we have only one variable.
yes,
As
because we are intentionally fixing others.
okay.
But when
That's
we
why it
fix
is.
others, yeah, when we fix others, we say that this link length is, let's say, 6 meters and it will not change.
Yeah, yeah.
Okay, this link twist is 0 degree and it will not change. This is how we are constraining these further. Okay,
Okay.
but if you say that everything can change, okay,
So it doesn't depend on the number of axes. It means
uh,
that's what I said that.
yeah, exactly. See, if you
Configuration.
say that all your links are rigid,
Correct, correct.
okay, then you can modify this argument to say that yes, it is equal to the number of axes. Okay, but the number of axes is not the fundamental definition of degrees of freedom.
It depends on the constants which one we are fixing.
Yes, okay, it depends on the total parameters. Okay, this is how the degree of freedom is calculated actually. You calculate the total degrees of freedom and you subtract the
Yeah.
number of degrees of freedom that are constrained.
Okay.
That
Okay.
is the that is the mathematical formulation of degrees of freedom. That, yeah, formula.
Okay. That's somewhere I. It means in YouTube I saw that in a matrices there is so many numbers of elements are there.
Yes,
In that we have some constants and some number. It means it is by subtracting that we are finding the degrees of freedom. It means by rotation. It means it was provided that that's suppose that R1, R2, R3 are there.
yes,
Along with that, if R1 it is 0 degree, R2
hmm,
R2 0 degree, R3
yeah,
R3 0 degree. It has having 111, and along with that, if it is aligned with along with that axis, it is 111. Remainings are zero.
okay.
With that 3 and 6 instead 9. If you subtract that, it will be 6. So we said that it is
Uh,
constants are 6 and elements are that. If you are subtracting that, it is provides the degree of freedom.
the argument is correct. The reasoning is not. Okay, why it is not? Because, acha, okay, tell me, why do you use a rotation matrix for? Okay, what do you use a rotation matrix for?
in order to provide the reference with respect to ground or the new axis.
No, like fundamentally we use the rotation matrices to represent orientations,
Correct,
relative
correct.
orientations between bodies, right?
Yeah, yeah, correct, correct.
And how many parameters do you need to represent the orientation? Yes.
Orientation X, Y, Z. Three.
Okay, you can specify orientation about X, Y, and Z.
Correct,
Okay, like what I am saying is actually also a not so correct argument, but you can understand it in this way, right? That you can rotate about X, rotate about Y, and rotate about Z to get any
correct,
orientation.
correct.
So how many parameters do you need to represent rotation, orientation? Yes.
Orientation.
Yes. How many rotations are we doing here?
It means it means about the Z axis. You mean to say that,
No.
or
See,
X
one
axis?
one type of rotation that sir has told you about
Okay,
is
yeah.
yaw pitch roll
So,
rotation, right?
correct,
So
correct.
how many total, independent rotations are you carrying out here?
Three.
Three. Exactly
Correct.
three. And
Hmm.
our argument is that when you do these three rotations, you will get, I mean, using this sequence of rotation, you can get any orientation you want, right?
Correct, correct.
Okay. So basically, to represent orientation, you need three parameters. But how
Hmm.
many parameters are there in a rotation matrix? Right? Like it's just a 3 cross 3 matrix, right? So how
3 +
many?
3.
Yeah. So how many total parameters are there?
Total 9 are there. It is
Yes, total
number.
9 are there. Okay, but
Correct.
I am saying that these 9 parameters, okay, represent these 3 parameters. So how is this possible? Okay, because now for these 9 parameters, there are 6 constraints. Okay,
Correct.
there are 6 equations that constrain these parameters. Okay, all of them.
Hmm.
So that is how, I say that yes, rotation matrix still represents the orientation, because in the end it can only specify 3 independent parameters, because it has to satisfy 6 constraints.
Correct.
Okay, and what are those 6 constraints?
Uh, that with respect to frames, it will then.
Okay, no. See, um, first rule of robotics is everything is easy, and if you think that something is complicated, okay, or if something is going to be complicated, then you might be thinking about it in a wrong way. Okay, so you might have studied that. Uh, wait, were you in the last class that I took?
I was late, bit late.
Okay, yeah. So did you attend the section when I told you that these column vectors are actually the basis vectors of the new frame?
Yes, yes.
This, yeah. Do you remember this?
Yeah, yeah.
Okay. And what is the condition on basis vectors for the coordinate frame that we choose? Okay, that their norm should be one.
Norms. I didn't remember. Actually, that
Their
what you
length
got
should be one, right? The
recorded session is not accessible to us.
no, wait. I did share it on the discussion thread, right?
I might have left that time because
No, you can join it again. All the emails will be there.
it was said that it will be shared on the course web page.
Yeah, it was supposed to be shared on the course webpage, but since
It,
it was
it
not
was not.
shared there till now, I just shared it on the thread itself.
Okay, okay.
Okay, so like you can see it there also, but it is true that these columns are actually the basis vectors of the rotated frame as
Okay.
seen in the ground frame. Okay, if you see these
Yeah, yeah, correct, correct.
vectors in the ground frame. Okay, but these, basis vectors, they have a length of 1. Okay, they are basically the rotated form of your I cap, j cap, and k cap.
Okay, unit vector.
Yeah, they are unit vectors.
Correct.
Okay, so what is the length of unit vectors? 1.
One unit. Correct.
And they should not change, right? Because you're only rotating them.
Correct.
Okay, so these are your three constraints. Okay, that the length of these vectors should be 1. Okay, and where are the other three constraints? They are here in the row vectors. Okay,
Okay.
because I told you this also, that these row vectors are the basis vectors of the ground frame as seen in the rotated frame.
Oh.
Okay, so these
Hmm.
also, because these are basis unit vectors, so these also should have magnitude of 1.
Correct.
So this is where your 6 constraints come. Okay,
Okay.
and a compact way of writing them, or a different way of writing them, is to say that R is an orthonormal matrix.
Correct.
Okay, so basically the R transpose is its own inverse,
Correct.
and the determinant of R, what should be the determinant of R?
One.
Exactly,
One
plus 1.
plus one. Correct.
Okay, it should not be 1.
Uh,
Yeah,
plus one.
it is 1, but yeah, because R is not just an orthonormal matrix. R is an special orthonormal matrix.
Correct.
Okay, that is why you will see this kind of rotation written in many places when you try to read, robotics books.
Correct.
That
It is
R is
written.
a part of the SO3 group. This is the spatial orthonormal group, not just orthonormal. And spatial orthonormal stands for this, you know, for matrices who have determinant plus 1.
Hmm.
Okay,
Correct.
yeah. So this is, how you say that. Basically, this is how you calculate degree of freedom. You have your total parameters that you are using to represent, and then you have your number of constraints, and then you subtract them, you get your degree of freedoms.
Okay.
Okay, any more doubts?
Thank you.
Yeah, sure.
Sir, just a second, sir.
Yes,
Where is the video of the previous class shared, sir?
I
Is it?
shared the YouTube link on the, I think, Google Groups thread of this course, the discussion thread.
Oh,
In the
yes,
course
sir.
website, there is an ask a question option.
Yes, sir. Yes, sir.
Yeah, so if you click that, I think it will open directly to the discussion forum that is on the Google group.
Oh, yes, sir. Thank you, sir.
Yeah, and in one of those, I don't remember exactly what email it was, but in one of those, I replied that this is the link, so you can find it.
Yes, sir. Yes, sir. Thank you, sir.
Yeah, sure. Um, anything else? If not, then let us close this session. Um, I will log off from this. Yep. Yeah. So you guys can leave now, and I will just close the meeting. Thank you.
Thank you, sir.
Sure. Yes, sound is quite less actually. It is the problem with my recording software. If you wear headphones and keep your voice at full, you might be able to understand actually what I'm saying. I'm really sorry for this. I'm trying to solve this, but it is what it is for now.